Every challenge question from the textbooks, part 11. This is the trig, the second of the trig chapters, I think. Anyway, we proved these things. Now, these are quite weird to prove because we don't have any actual maths with which to prove these. Like, we can't use compound formulas or Taylor series or anything that's actually properly maths. So what we have to do is just get out the cast diagrams that they like using and define the vertical distance in the unit circle from some angle theta to be sine of theta. So this distance here is sine of theta. But of course, this angle here is 180 minus theta. So therefore, sine of 180 minus theta is also this height, which of course is symmetrically the same as this height. So therefore, these two things equal the same. And likewise here, cos of minus theta equals cos of theta. Cos is talking about the horizontal distance that you go along with angle theta to the unit circle. And so cos of theta is this horizontal distance. Cos of minus theta is this one as well, which means cos of minus theta is also equal to cos theta. And finally, tan. Now, tan is a little bit more tricky. Tan is actually talking about the gradient of this line, which of course is rise over run, so that's a over b, which is why it's sine theta over over cos theta. And you can see that the gradient of this line is a over b when you've got theta. And then when you've got 180 minus theta, which is all of this angle, you've got this gradient here, which is a over minus b, which is therefore just minus a over b. And we get tan of 180 minus theta is minus what tan theta was. And that's kind of, I think, at this point, the only way that you could, quote unquote, prove that idea. Anyway, this is a pretty interesting question. We've got a bunch of triangles in here slotted together. The first thing we can do is work out some stuff here. So CE, well, this is just, tan 30 is just this over that. So 1 over tan 30 is this. 1 over tan 30 is 1 over root 3, which is root 3. DC is this length here. We can do some Pythagoras. This squared plus this squared equals this square rooted, which is 2. And then BC is this length here. Bit more work to do here, I guess. But what I did, I think, was I just used a bit of Pythagoras at some point. I can't even remember. Oh, yeah, you notice this is quite nice. Look at the entire triangle. It's 90 degrees here, 45 degrees here. So this is 45 as well, which means this is isosceles and right angled. So those two are the same. And that's obviously super helpful because this length across here is 1 plus root 3. So we can call each of these lengths x because we know they're the same. You have x squared plus x squared equals 1 plus root 3 all squared. Expand this out, collect these together, divide by 2, and you get this as your BC length. At that point, to find DB, which is this length here, you can just do 2 squared, take away what we just found squared, which is of course just the inside of this, and square root that answer, and we'll get this answer here for DB. State the size of BCD. I've already argued that this is 15, because this whole thing is 45. And then find the exact values of sine 15. So that's opposite over hypotenuse. So sine 15 is this over that. And cos 15 is therefore this length, which we said was this one over that one. Over the hypotenuse, which is also 2. And we'll end up with those two things there. So pretty cool question there. We just need to make a substitution for this question. So maybe x equals 3 theta. Change that to a 3 theta by timesing these by 3. And replace it with an x. And our new question is look for solutions to cos squared of x minus cos of x equals 2. Between these two bounds, of course, move the 2 over, and you notice this factorizes. So we're looking for cos of x equals 2, or cos of x equals minus 1. Of course, cos of x equals 2 has no solutions. Cos of x equals minus 1, we can inverse cos to get this principal solution of 180. And actually, you can just draw the cos graph. I was really lazy today, didn't bother to draw anything. But so 180 is the first one. And then you add 360 to get the next one, which will actually be 540. And then you take away 360 to get the one before, which is minus 180, and then take away another 360 to get to minus 540. And those are the 4 answers, except remember the substitution. So 3 theta equals this. And we divide all of them by 3. And we end up with our 4 answers just there. Number 2 is very similar. Make the substitution x equals theta minus 45. Take away 45 from these things here. Replace it with x. Now this is the bound we're looking for, and we're doing tan squared equals 1. Square root both sides to get tan x equals plus or minus 1, and then we've got 2 jobs to do. Either solve tan x equals 1 or tan x equals minus 1. Principal solution to that is 45, and then for tan you just have to add 180 a bunch of times or take it away, but that's not within the range, so just add 180 once. If you do it again, you're out the range, so that's fine. Inverse tan of that will give you minus 45. Add 180 to get this, and add another 180 to get this, and those would be our 5 solutions to this question here. Oh, sorry, no, they're not, because we have to do the substitution back again, don't we? So add 45 to all of these, and we end up with those quite neat, nice solutions there. Another one here, I think this is the last one. This is factorizable, and if you're ever having trouble spotting a factorization, just replace the annoying trig thing with a letter. And if you're still having trouble with that factorization, replace the power 4 and 2 with just power 2 and 1. And hopefully this now brings us all the way down to something that we factorized back in year 8. And you just apply it to here, you replace these with x squares instead, and replace these with tan squares instead, and you get your factorization. Of course, now we have that either tan squared equals 2 or tan squared equals 1. The good news here is that we've already solved tan squared equals 1, and we got all of those solutions. So I'm not going to do that again, I'm just going to say that's correct. And here, solve tan squared equals 2 by moving the 2 over and square rooting, and then just looking for, again, separately, tan x equals root 2, tan x equals minus root 2. Do inverse tan to get the principal solution, inverse tan here to get that principal solution, add 180 to this one, add 180 to that one, and we end up with all these answers, and I think that's the entire chapter done.